Well, this is our final project for AI at Auburn, and we decided to make a AI poker bluff detector. So basically, we happened on this idea because bluffing is really common in poker, and it's a technique that's used by a lot of players to push people out of the play and basically trick them into giving their money. And so essentially what they do is they pretend like they have really good cards and convince other people to fold. Um, basically, this is a interesting problem for poker players because it's hard to tell when someone's bluffing, and you're trying to guess based on like how they're betting, how they appear, and then even just like how your gut feels. But none of this is really backed by science. And then there's also tools that can kind of train people to look for this, but they don't really focus on the past behavior of opponents. So this is why we decided to try and answer this question. Can an AI model learn to detect bluffs considering game data and past actions?
So for the existing approaches that are already out there, with AI and poker, it's usually just AI is trying to play poker itself, just trying to get an optimal game flow. And there are very few like works out there that focus on like actually detecting bluffs in other players. So some of the past work usually works with facial recognition for bluffing. They use software called OpenFace and also CNNs to try and determine if people are bluffing or not. There was also a study based on the annual Computer Poker Championship, which used statistical features. However, it's not as popular of a study as the accuracy levels were not as high as people were hoping. And then also there's deception detection used in courtroom videos, which kind of links to how bluff detection would work in poker because it uses facial recognition and like how people look to try and determine if people are lying or not. And there are already like a lot of severe limitations in the existing approaches. For example, there's a lot of video data that's needed so far as it focuses on how people look whenever they're trying to bluff. And then there's a limited sample size, and oftentimes the existing approaches are not very accurate.
So for our approach, the first thing that we had to figure out is what we were going to define as a bluff, because there's so many different hand and playing combinations in poker, and we wanted to have a really narrowed down definition of what we were going to focus on. And so what we decided was that we were going to focus exclusively on games that went all the way through to the fifth round or to the fifth card, um, where a player either called a bet or raised on top of an existing pot with only a high card. And this was to ensure that they were playing with bad cards and actually adding value to the pot. So the first thing we had to do was the first thing we have to figure out was our game data, because we couldn't use video or audio data. So we had to actually figure out simulation environments using PyPoker and trying to actually make simulated agents that played with different strategies. Then we also had to work with labeling the different rounds and who was bluffing and who was not bluffing, and just looking at the hand strength and betting actions. Okay, so for simulating the poker games, we developed a bunch of different somewhat simple models, and had them play against each other randomly. Every game had four players, and like I said, it could be any of these agents, and one agent could play against another version of the exact same agent, with up to four of the same type of agent being possible in the same game. So our bluffing agents, we had one and two. One was more focused on actually playing with bad cards, and the other one was focused on the actual strength of the board. We had a tight agent that played based on having the top 20 starting card, top 20 starting pairs. We had a random agent that just played randomly, a fish that kind of followed the behavior of others, and then a GTO that tried to follow GTO charts, which is game theory optimized charts, and also play within certain hands or certain hand strengths on the board. Um, so we ended up simulating about 350,000 rounds using these agents, which is a bunch of data because we have data for each agent. And then in each log for the rounds, we have the agent's whole cards. Then we have the cards that were on the board, their betting sizes and actions, and then also we calculated their hand strength and board strength.
For data encoding, from the simulation of poker games, we were left with several raw poker logs, and this data was very rich in terms of it had everything we you would need when analyzing a poker round. We had the different agents and what kind of agents they were based off of the agents that John just described. We had all of their actions for each street, which is part of a poker game. It starts from the pre-flop, then the flop, then the turn and river. So all those actions for each agent. And then we also included the whole cards of each agent as well, which are the two cards that are given to an agent when the poker games start. And then there were also in this data, in this round data, the board texture was there as well, which is, how good of a board like the board is, which means how many like possibilities like can people have and such. So with that, the raw simulation logs were converted into a fixed length feature vectors with the following attributes. One hot encoding to represent actions and cards, the board texture analysis, like I mentioned, and normalized bet sizes, right? So with normalized bet sizes, we use 10,000 chips, right? So if somebody bet, let's say, 1,000 chips, right? That would just be a normalized bet size of 10% or zero point 0.1. And each hand was then labeled as a bluff or not. An agent was set to bluff for that round. And each feature vector had a fixed length of 375. And for the machine learning model, we use a PyTorch-based neural network. So like I mentioned, each feature vector was 375 features long. And I forgot to mention this, but we have 350,000 rounds of data, but we created a data point for each agent, whether they bluffed or not for that round. So in total, we had 350,000 times four. So we had 1.4 million data points. So the way we initialized our model architecture was we had the four hidden layers, like mentioned here. We had batch normalization, which kind of it prevents having exploding and vanishing gradients. We had a dropout layer, which kind of it drops out a random percentage of the neurons in each layer. And what this allows you to do, or which allows the model to do, is like it allows it to for all the nodes to kind of learn equally. So like not one node is like forced to learn more and forced to be activated more than like the other nodes. And then we have a ReLU after each layer to add that nonlinearity, right? And then for the training setup, we use binary cross entropy, which is kind of standard for which not kind of, which is standard for binary classification. We use the Atom optimizer, which is probably the best optimizer out there. And then we use an 80-10-10 split, which is 80% for our tests, sorry, 80% for our training data, 10% for our test, and 10% for our validation. And we use something called early stopping, which means that we would train for an epoch, and then we would check to see if we would check our model on the validation data. And then if we happen to see like really good validation loss, we'll save that model, right? And let's say in the next three epochs, however, our best validation loss hasn't increased. So our model hasn't gotten better at all. Then we stop training and then we save that. Then we stop training and we go into testing. So evaluation results, once we found our best model, We tested it on the testing data, and it evaluated to 81.15%, which is pretty decent. And the model successfully does the following: it recognizes bluff patterns, maintains generalization, and detects deception bluffing from structured data alone. This helps confirm that action and context data is highly predictive, which is kind of like what we're going for. We wanted to see if, given all this highly detailed round data, can we train a model to predict whether an individual is bluffing or not?
So for the comparison to existing work, like we talked about before, unlike the more common facial analysis models, our model can just basically use the game logs, allowing it to be a lot more faster and a lot more scalable. And additionally, it can get similar or better accuracy levels to most compared to most models, as it's running more on more concrete data, as opposed to just things that can change a lot, such as facial analysis. Our model also includes action sequencing, bet size normalization, and multi-agent behavior, which is improvements compared to the other facial analysis models. And our work overall has pretty similar levels of promising future when compared to most other existing works already out there. So as for what we learned, we were able to learn that bluffing behavior has a very detectable structure in terms of the data itself. As we can see, like when we passed all the data logs through with a very high accuracy level, we were able to see if bluffing was if we could predict bluffing or not. And then we learned that data cleaning and encoding is a very critical part of having a or well-performing machine learning model. If we didn't clean up the data very well, our machine learning model would not only take a longer time to run, but also more than likely be less accurate. The simulated agents can also produce meaningful bluffs if given correct parameters. So data can easily be generated for many different purposes. So say that you want to do something besides bluffing. For example, like say you want to see if someone is raising like accurately or if they're trying to like over raise or anything. You can kind of use simulated agents to kind of do that same thing. And then board and betting context along with or can help power bluff detection. So it's very important to look at past data and just like the board in general. And it's important to have a context uh, for bluffing. So for the challenges in future work, there's not a lot of real world bluff data or labeled bluff data out there, which is part of the reason why we chose to develop our own data. So that was one of the challenges. And then additionally, agents can't fully replicate the complex human way of thinking, along with emotion and the ways of speaking that can sometimes be a telltale sign of bluffing. So that's like another thing that we think that we could try and improve on. So for future ideas. In addition to using the poker logs, we could integrate existing facial and audio bluff detection to help improve the model and just make it overall stronger. We could use LSTMs for better action sequence modeling, and also we could train on real world poker logs for more of the human interaction to be available. And so, in conclusion, we were able to build an end-to-end AI pipeline for bluff detection, in which we first simulated games, then we encoded the features considering those simulated games, and then we were able to finally train classifiers. And then with this, we were able to achieve around an 81.15% test accuracy. And overall, this project helps prove that AI can learn bluff detection from just structured gameplay alone. And this project can overall help open new doors for the future of AI poker tools.
So now we're going into our demo. But before we go into our demo, real quick, I just kind of want to piggyback off of what Roshan said, how our model is very has reasonable accuracy for detecting the agents specifically that we design. So it might not fare well with like actual human players. And this is the limitation that we had to come to terms with because this would mean that we would have to develop very, very real uh, agents that displayed human behavior, which was not very practical or plausible the with the current project. So we developed pseudo real agents, and our model happens to detect bluff well for those pseudo real agents. And now for the demo here, like Roshan mentioned, our project is split into three different parts. One is the simulation, one is the encoder, and then one is the actual model. And John, if you want to go through and explain the simulation part of this.
Yeah, sure. So basically, you can go ahead and scroll down a little bit.
Yeah, yeah.
Um, yeah, so we just had this is for our tight agent. These are just the best possible hands, and then this was for our GTO agent. Um, and so then we also used two different libraries for this. We used PyPoker and we used trays. So we needed to, and they represent cards differently, so we had to switch between those. This would be our board function for calculating the strength of the board. So we looked at two things. One was the texture, and essentially what that means is if the board has a lot of like straight or flush potential, then it's considered a
Mhm.
wet board, and if it's got nothing of any value, it's called considered dry. And it also has connectedness score for how close the cards are. And so next we have all of our agent blocks,
Yeah.
which we don't need
We
to
can
get
kind of,
into
yeah,
too
we can just
much.
skip over that. And then now we have our run block here.
Yeah,
And
so this one we have it set so it picks any random agent from above. So like I said, it's possible for four of the same agent type to be playing against each other. And we have different weights assigned to them in terms of their playing. We wanted the GTO and the bluff agents to have more prevalence in the rounds because we wanted to increase the amount of bluff data we had. Um, and yeah, I guess we'll just wait for this to run. So um, this will run how many rounds? Let's see.
this will run only 10,000 rounds or 1,000 rounds, sorry.
Yeah, so it'll run 1,000 rounds with these simulated agents. And if Sujay can scroll down really quick, it's running right now.
Yeah.
So
Yeah.
you can
We
see that it
have,
generated a bunch of this data.
so So here it generates 1,000 rounds, right? And you can tell here it kind of goes in the flow of the game. Um, Let me scroll all the way up. Like it shows which each of the agent's cards, the agent type, tight agent, random agent, GTO agent, bluff agent, and it says the pre-flop started. It tells what each agent does in each street, pre-flop, flop, turn, river, and then it tells who wins the round and what their stack looks like after that round. And yeah, John, do you want to add anything else?
Yeah, I mean, you pretty much covered it. That's how we got the data. We encoded pretty much all of that information.
Mhm.
If you want to go on to the encoder really quickly.
Yeah, yeah. Oh, the encoder file.
Yeah.
Yeah.
So
So
yeah, you got it.
yeah, yeah, I got this one. So for the encoder here, for each round, we wanted it to include a couple parts, right? The first part being um just the agent's actions, just that agent's actions, and specifically the last eight, right? And if they didn't have eight actions in the round, then we add some padding to the left of that, padding of zeros, and then here we have the whole game flow of all agent actions, right? And then here we have the normalized stack size for the agent, right? So if the agent currently has, let's say, 10,000 chips and they start with 10,000 chips, that means their normalized stack size is one, right? Or if they have 8,000, their normalized stack size is 0.8. And then here, the encode river, this is just a multi-hot encoding of length 52, and there'll be a one for if for the board cards, if there's a card that showed up, let's say um King of Hearts, right? Then there'll be a one in the position corresponding to King of Hearts in this multi-hot encoding. Then we have the connectedness score and the witness score. Like John mentioned, witness score is just like how many possibilities you can do with the cards on the board. And then the connectedness score um is the straight potential, like if you could have a straight flush or just a regular straight. And yeah, so that's how we encode everything. And then we take in all of our files here. The old data and Bluff data, these are the files our um of our simulations, right? And then we encode all that, and then we compress it into one um NumPy compressed file called dataset.mpz. And then once we get dataset.mpz, we load it in here and shuffle the dataset. We split the data to train, validation, and test. 80% training, 10% validation, 10% test. And then we create a PyTorch dataset. We create a data loader, and then we define our neural network here. And this is what I mentioned with 4 hidden layers. Um, we have the batch normalization, the ReLU, the dropout, and then in the very end, we have our sigmoid to give us a normalized value between 0 and 1. And then we train our model, and this includes the early stoppage right here. And as you can see, it was supposed to run for 30 epochs, but instead it only ran to 17 because it stopped early.